Design every Mars mission with the assumption that dust will eventually reach every exposed surface, every mechanical joint, every optical sensor, and every power system. Martian dust is not merely dirt carried by wind. It behaves more like an invasive environmental hazard that interacts with machinery, electronics, thermal systems, and even human physiology in ways that are difficult to fully predict on Earth. Successful exploration depends less on avoiding dust storms and more on engineering systems that can continue functioning while constantly exposed to them. One of the most important realities to understand is that Martian dust particles are extraordinarily fine. Many are smaller than typical grains found in Earth deserts and have sharp, abrasive edges because Mars lacks liquid water and weathering processes that smooth particles over time. This means dust behaves almost like microscopic shards of glass. Over months and years, it can erode seals, scratch camera lenses, damage solar panels, and wear down moving components. Mechanical systems intended for long-duration missions should minimize exposed joints and reduce unnecessary moving parts whenever possible. Electrostatic behavior creates another major challenge. Mars has an extremely thin atmosphere, and dust particles easily accumulate static charges through friction and solar radiation exposure. Once charged, the particles cling aggressively to surfaces. Solar panels are especially vulnerable because even thin dust layers can dramatically reduce power generation. This issue became one of the defining operational limits for earlier Mars rovers. Practical mitigation strategies include electrostatic dust repulsion systems, vibrating panel surfaces, compressed gas cleaning systems, and tiltable solar arrays that encourage passive dust shedding through gravity and wind interaction. Power planning should never rely entirely on solar energy in regions prone to severe storms. Global dust storms can reduce sunlight for weeks or even months, transforming daytime conditions into dim twilight. Missions that depend exclusively on solar panels risk catastrophic power loss during prolonged storms. Nuclear power systems such as radioisotope thermoelectric generators offer much greater reliability because they operate independently of atmospheric conditions. Hybrid systems combining nuclear backup with solar infrastructure may eventually become the preferred architecture for human settlements. Thermal management becomes significantly more difficult during dust storms because airborne particles alter atmospheric heat transfer. Dust absorbs and scatters sunlight, cooling the surface during the day while trapping heat at night. This creates unusual temperature dynamics that can interfere with habitat insulation, battery efficiency, and instrument calibration. Exploration systems should be designed with flexible thermal control systems capable of adapting to rapidly shifting environmental conditions rather than relying on narrow operational ranges. Navigation during storms presents both technical and psychological challenges. Dust can reduce visibility to extremely low levels, limiting surface mobility for rovers and future astronauts. Traditional visual navigation systems become unreliable when landmarks disappear behind suspended dust clouds. For this reason, future exploration vehicles should integrate multiple navigation methods including radar mapping, LiDAR, inertial navigation, and satellite-assisted positioning. Redundancy is essential because dust accumulation may temporarily disable individual sensors. Human exploration introduces an entirely new level of complexity. Martian dust is not just abrasive but potentially toxic. Some dust samples contain reactive chemical compounds such as perchlorates, which can interfere with human biology and damage respiratory systems if inhaled. Habitat air filtration systems must therefore operate continuously with extremely high efficiency. Airlocks require advanced decontamination procedures to prevent dust from entering living environments. Suit designs should minimize direct exposure by using external docking systems where astronauts enter and exit through the rear of the suit rather than bringing contaminated equipment indoors. Surface mobility systems require special attention because dust infiltration can gradually immobilize vehicles. Wheels, bearings, actuators, and suspension systems must tolerate continuous abrasive exposure over long operational periods. One effective strategy involves magnetic or electrostatic dust barriers around critical components. Another involves modular replacement systems that allow worn parts to be swapped robotically without requiring complete vehicle disassembly. Communication reliability can also degrade during severe dust events. Fine atmospheric particles affect radio wave propagation and may interfere with optical communication systems such as laser-based data transmission. Exploration networks should maintain multiple communication pathways including orbiting relay satellites and locally distributed surface repeaters. Maintaining communication redundancy becomes especially critical for crewed missions operating far from central habitats. Weather forecasting on Mars remains far less mature than terrestrial forecasting. Dust storms can form rapidly through localized, atmospheric instabilities, and then expand across enormous regions. Continuous atmospheric monitoring from orbiters, aerial drones, and surface stations is essential for early detection. Future missions will likely rely heavily on machine learning systems trained to recognize subtle atmospheric changes associated with storm formation. Predictive modeling may eventually provide crews with several days of warning before major events develop. Landing operations become particularly dangerous during active dust conditions. Dust obscures terrain features and interferes with optical hazard detection systems during descent. Fine particles kicked up by rocket exhaust can create dense clouds that reduce visibility and potentially damage spacecraft surfaces. Engineers are exploring solutions such as pre-prepared landing pads, autonomous terrain relative navigation systems, and landing engines designed to minimize surface disturbance. Dust also affects scientific operations in surprisingly complicated ways. Instruments studying atmospheric chemistry, geology, or astrobiology may produce distorted readings if calibration surfaces become contaminated. Optical instruments can suffer reduced sensitivity over time due to dust coatings. Long-term scientific missions therefore require self-cleaning mechanisms, calibration redundancy, and maintenance protocols designed specifically for dusty environments. One of the more subtle operational concerns involves psychological effects on astronauts during prolonged storms. Global dust events can block sunlight for extended periods, creating dim and monotonous conditions inside habitats. Combined with isolation and confinement, this environment may increase stress and fatigue. Habitat design should therefore prioritize lighting systems that simulate natural circadian rhythms and provide psychological comfort during long storm periods. A practical long-term strategy for Mars settlements may involve partially underground habitats. Subsurface structures naturally shield occupants from radiation, thermal fluctuations, and dust infiltration. Lava tubes and excavated regolith shelters could significantly reduce environmental exposure while improving habitat stability. Surface infrastructure would still remain necessary for energy generation and transportation, but critical life support systems could be protected beneath the surface. Robotic precursors play an essential role in addressing dust-related challenges before humans arrive. Autonomous maintenance robots capable of cleaning solar arrays, inspecting equipment, and replacing damaged components could dramatically improve habitat resilience. Future Mars exploration will likely depend on cooperation between humans and robotic systems, with machines handling many of the most hazardous maintenance tasks during storms. Materials science remains one of the most important areas of advancement for overcoming Martian dust hazards. Engineers are developing dust-resistant coatings, self-healing materials, advanced ceramics, and electrostatic shielding technologies specifically designed for Martian conditions. Even small improvements in surface durability or dust repellents can dramatically extend mission lifespans when accumulated over years of continuous exposure. The broader lesson from Martian dust storms is that Mars is not simply a colder version of Earth. It is an active planetary environment with its own atmospheric dynamics, chemistry, and environmental threats. Dust shapes nearly every aspect of exploration strategy, from power systems and habitat architecture to human health and scientific operations. Missions succeed not by eliminating the problem, but by designing systems capable of adapting to persistent environmental stress. Every storm sweeping across Mars carries traces of the planet's geological history, lifting ancient particles into the atmosphere and redistributing them across vast distances. These storms are not interruptions to exploration. They are part of the environment itself, one of the defining forces that any long-term human presence must learn to endure, predict, and eventually work alongside.